Welcome back. Thank you very much for just doing that quick transition. I know we only have about 5 minutes, but we are nearing the end of the term, nearing the end of the course material, and my goal is to try and get the electrochemistry unit done by next Friday. So that means using the available time I've got. And I've got a few demos next week to pass to entertain us. Hopefully ones that don't go boom. Or maybe we want ones that go boom. I'm not really sure. This is the modules, the subsections from the chapter 19 on electrochemistry. And if you follow through my course material, the textbook is there to expand on the material I provide. I'm going to hit the highlights of the course material and the problem sets, and my course material is kind of where I draw exam questions from. So if you know those well, you'll do fine. If you want the filler or background information or more detailed explanation, the textbook is a good resource for that. So this is the material that we're going to be covering in this section. What we have is this figure from thermodynamics. Thermodynamics and electrochemistry are linked as well. And we're going to determine what that relationship is, just like the relationship between thermodynamics and equilibria. We have work that is done here. We have, for spontaneous processes, the maximum work that can be extracted and still have a spontaneous process, and the minimum work that must be done for the system to make it spontaneous. What we're doing now is we are just extracting that free energy as electrical energy. And the pressure volume work, where you have an expansion and a cylinder and we have a combustion engine, that has efficiencies around 30%. Electrical energy has efficiencies pushing 100%. And so electric vehicles, which are coming on stream as we speak, are going to have a much higher efficiency, use less fuel energy to go the same distance. I am not sharing my screen. Oh, how does that sound? Is that better? Sorry about that. Thank you, Alex, for pointing that out to me. Just looking at the time. Okay, we're going to do one more slide just to take us to a nice stopping point. And that is to look at the types of electrochemical cells. We have a galvanic or a voltaic cell. Its terms are used interchangeably, proceeds spontaneously. Battery, oxidation. We had the reaction we just did in the fume hood with regards to the aluminum can. That was an electrochemical process that oxidized the aluminum of the can. That's a spontaneous process. An electrolytic cell is non-spontaneous. So things where we need to put energy in, electrical energy in, are electrolytic cells. If we want to electrolyze something, if we want to electroplate, or if we want to use electricity to synthesize, the creation of hydrogen and oxygen from water uses electrolysis. That's an electrosynthesis process to break water down into hydrogen and oxygen. And finally, more in the analysis realm, we have what's called a concentration cell. A concentration cell has the same electrodes and reagents in each of the two different half cells, but they're at different concentrations. And from that, we can determine information about excuse me, one cell or the other. So a pH meter, many meters that you deploy in environmental science, in monitoring systems, are even in industrial applications, they're concentration cells that measure whether it be pH, atmospheric reagents, that type of contamination, that type of idea. They're concentration cells, possibly. That's where we're going to leave class today. And when we come back, we're going to delve more detail into redox reactions and then look at galvanic, electrolytic, and concentration cells with numerous examples that shows the calculations and the applications of these in many real-world things. So that's it for today. Thank you very much for your time and attention, and to the people that are coming to help clean up the fume hood, right? There's you. You're coming. Sweet. Anyway, thank you very much, everybody. Have a great day.